Okay, so like I said, we're going to go back and try to finish. We'll see the rest of chapter 11 there. So this is, we're going to talk about alkenes and alkynes, and these are what are referred to as being unsaturated hydrocarbons. If you remember, saturated hydrocarbons are basically compounds that have the maximum number of hydrogens per carbon, which basically means they're all single bonded. So unsaturated hydrocarbons basically means that there's at least a double bond, maybe a triple bond. You really don't have the maximum number of hydrogens as possible. So alkenes, the functional group of an alkene is really the carbon-carbon double bond is the functional group. While alkynes, the functional group is the carbon-carbon triple bond here is the functional group. And these guys have sort of general formulas of CnH2n, and it's 2n, not the +2 like we see in the alkanes because of the double bond, so we lose those two hydrogens. The alkynes have CnH2n -2. It loses two hydrogens from the alkane plus another two for the triple bond. That's like a difference of 4 hydrogens basically from the alkane in this case. Alkenes and alkynes, they basically are also named off of the first 10 alkanes, except with a little bit of difference in the ending part here, ENE, YNE, ENE for our double bond and YNE there for our triple bond. So if we look at this guy, which is our alkane with 2 carbons, that is ethane, ANE. If we lay up a double bond there between the 2 carbons, we will lose 2 hydrogens, 1 on each carbon. And we will end up with an alkene, which will be ethene, ENE. And if we lay up 1 more bond there to get us to a triple bond, we will once again lose another 2 hydrogens, 1 from each carbon, and we become ethine, YNE, at the end. So again, these guys, much like everything else, pretty much named after those first 10 alkanes. Now, unlike alkanes and kind of similar to alcohols that we just talked about, it is a double bond and triple bond that really is sort of the priority in terms of numbering and when you name it and stuff like that. So it's always a double bond or triple bond that needs to get sort of the lowest number when you go about naming it. Also, very much like the alcohols, once there starts to be really more than one option where you could put the double bond or the triple bond, you also need to give the location of where the double bond and triple bond is, very much like we did with the OH group, like 2-pentanol. You need to go like, 2-pentene to give the location of where those double bonds and triple bonds. So with double bonds and triple bonds, right around like 4 carbons is sort of where you need to start inserting the number into the names of it. Before that, like this guy here, there's really just one place you could put that double bond, so there's no necessary to put a number. And same thing here, there's really just one place where you could put that triple bond in that particular compound, so you don't need to give a number for that particular guy. Any questions on that there? Now, identifying alkenes, again, they gotta at least contain a double bond. The result of that double bonding is it actually cuts down on the sort of zigzag shape we talked about with the alkanes because of the tetrahedral geometry. What we end up getting if we look at this guy is 1 electron pair, 2 electron pairs, and 3 electron pairs. And we also have 1 bond, 2 bonds, and 3 bonds. And that is our trigonal planar geometry. And that's 120 degrees. So it makes like a triangle happening here is our geometry that we actually see. And that again is different than the geometry that we see here. It wants to update every day here. All right, remind me later. No more updating, please. There we go. All right. Now with our sort of triple bond, we also get some different geometries as well. Ethene is important as a plant hormone promoting ripening. So we do see these things in sort of commonly identified stuff. When we look at alkynes, again, that triple bond also changes the geometry that we see. So if we look again at this carbon, 1 electron pair, 2 electron pairs. Remember, double bonds and triple bonds count as just one, right? What we talked about was geometry, and also 1 bond and 2 bonds. So what happens when we get the triple bond is we actually get linear geometry, 180 degrees that happens with these guys. So your sort of line structure straightens out a lot of times when you have a triple bond in it, just kind of goes straight because of the geometry that occurs there. Basically just a straight line happening straight across that. Any questions on the geometry differences? So alkanes typically have tetrahedral geometry, leaning to that zigzag shape. Alkenes have the double bond, so they have the trigonal planar, more of that triangle type shape. And again, with our triple bond, it get out more linear as you go through those guys. So let's identify each of these as an alkene or alkyne. So the first guy is it is an alkene, right? If I could, right, I'm just going to scratch alkene. There we go. And this would be, so it would be an alkyne, right? With the triple bond that's happening here. If we wanted to give a name of the first guy, let's see here. This would have how many carbons, that first one? I'll trust you. 1, 2, 3, 4, 5, 6, 7, and 8. So it is 8 carbons. So 8 carbons would be based off of octane. Because we have the double bond, it becomes octene, ENE. And we do need to give the location of where that double bond is. So just visually looking at it, you can see if you go left to right will be the smaller number, right? And that double bond starts at carbon number 3. This would be 3-octene. Bless you. Why don't you take a shot at this guy and see what you think? Octine, right, from octane, and that would be 1. This group here is hanging off of carbon number 4 there, which would be 1 carbon, 2 carbons, 3 carbons. So that would be 4 carbons. 3 carbons would be propane, be a propyl group. So this would be 4 propyl, 1 octine in that case. Question on that name. Just weirdly drawn. All right, we'll go with that. All right, so they can kind of see the naming is very similar to what we have done before. Again, the double bond, triple bond takes that priority in terms of the numbering. So as we just kind of went through there, the IUPAC way of naming, we're going to swap out the ANE for ENE for our guys that have double bonds. Now, you could also have ring structures that have double bonds. So for example, this again is based off of cyclo. That would be cyclohexene because it has a double bond. Not to be confused with cyclohexane that has no double bonds, and not to be confused with benzene that has 3 double bonds. So this would be cyclohexene. Any questions on that there? All right, so why don't you give this guy a go and see what you come up with. And while you're at it, why don't you draw 3-chloral. What's that? No, I'm gonna give you a name so you could draw it. So name the guys on the left and draw. Let's do 3-chloral 2-hexene. Let's do 2,4-dimethyl 3-heptine. Clearly just making it up here in my head. I'll hope for the best. All right, names on the left and some structures there on the right. Look, so starting with A, looks like 1, 2, 3, 4, 5. And there's a couple different ways you could get it, but I think that should be our longest continuous of the double bond in it. So 1, 2, 3, 4, 5 would get us hexene, not a pentane. I know, I failed chemistry. It's okay. There you go. It should be pentane, yes. Just my head was, thinking about a different question. I suppose pentene would be good. That's more like 5, I suppose. Here we do need to give the location of where the double bond is located. And again, you can hopefully see just going left to right will get you the smaller number for that double bond. And that means that this is 2-pentene with a group that is hanging off right there, which is a methyl group. And that would be 4-methyl 2-pentene on this exact one here. Question on that one? Yeah. Bond is that carbon number 2 is where it starts. Yeah. So you always want to give, again, double bond, triple bond priority in terms of the numbering, and you want the lowest number. So it's basically where those guys, which carbon they start at. And then obviously based on whichever way you number to do that, everybody else gets locked into the same numbering. So that's why the methyl stays at carbon number 4. It does not. So in the case of alkanes, because really the most important thing is kind of the groups that are attached, because they're all single bonded. It's the groups that takes the priority in terms of numbering. When you get a double bond or triple bond, since that's really the functional group that's happening for each of those guys always take the priority in terms of the numbering, whichever way gives those guys the smallest numbers, and then everybody else is numbered accordingly. And it's the same thing what we just did with the alcohols. The OH group takes the priority in terms of the numbering, and then everybody else gets numbered according to whichever way you need to go to give that guy the smaller number. So basically, it's always the functional group that takes the priority in terms of numbering, except for alkanes, because some people don't consider it having a functional group, even though some people call it the carbon-carbon single bond. But so the groups are sort of the most important thing. If you happen to run into a tie, whichever way you go, it's the same number, then you would want to go to the next important thing, which would then be the groups that are attached, whichever way we give those groups the smallest number. But if there's no tie and one way is a smaller number for the double bond or triple bond, you want to go that way for sure. Other questions? All right, so this guy is just basically straight across, I think, here. So We got 1 carbon there, 2 carbons, 3 carbons. The one I missed on the last one, 4 carbons, 5 carbons, and actually 6 carbons that are there. So that is obviously based off of hexane. Here we got a triple bond happening. So that is going to be hexene, YNE. You could hopefully again see going right to left here is going to give us the smaller number. Rolling that way, and that would be 2 hexene. There's really nothing else attached there, so that would be it. Question on that one? Now that we have the name, we're going to work backwards. So hexene, hex means we should draw 6 carbons. Go one more this way. ENE means it's a double bond, and it is at carbon number 2. So I'm going to again go left to right, but you could go right to left. It's your choice. So I'm going to lay my double bond right there at carbon number 2. That takes care of that. Because I went with this being carbon number 1, that means right here is carbon number 3, and I should have a chlorine. And you could write it on top or the bottom. It doesn't matter, whichever way you want to write it. And again, just like that, everything else is going to be hydrogen. So guy at the far right there needs 3 to get the 4 bonds. Guy next to him needs 2. Guy next to him needs 2. Guy next to him needs 9. Guy would need 3 in that case. That obviously would be the condensed formula, what we just drew there. Yes. You didn't get how we got there, or? Yes. Yeah, there's nothing else attached. Yeah, so this entire thing is the main group, and there's nothing else there. So it's all made up of the 6 carbons with the double bond. Other questions on that? Yeah.
So when it's double bond like that, it's like a bullet point on each side, right?
What's that?
Number B at 1, 2, 3. So when it has a double bond, it's kind of bullet point start. So it'll be 1 point, 2 point, and 3 point. The double bond.
I'm not sure I understand. Are you talking about line structure, or are you talking about this?
The line structure.
Oh, the line structure. Yeah. So if we were doing that 1, 2, 3, 4, 6, so you would start with the 6. That's really badly drawn. 1, 2, 3, 4, 5, 6. Tired 6 carbons there. There we go. So you do something like that. 1, 2, 3, 4, 5, 6. And then the double bond here was at carbon number 2. So you would just draw like an extra line there. Is that what you're asking? And then you would put the chlorine coming off of there. This is single bonded. I just drew a bad line there. What's that? For B. Carbons, you're talking? So there's carbon right here at the very beginning. Carbon right here before the triple bond. Carbon right here after the triple bond. Carbon right there, and carbon right there. So it kind of looks weird. I missed it on that first one we did because it's just straight. So you might think the triple bond's just kind of hanging out like in the middle, and it's like between these two guys. But there's actually carbons on either end of that triple bond.
If that triple bond, single bond would be the same.
If it was a single bond, it would actually be more the zigzag shape because of the triple bond. It linears it out, so it makes it a little bit harder to maybe recognize those extra ones that are there. Yep. Other questions? Okay, so heptine is 7. Yes, I regret that already. 1, 2, 3, 4, 5, 6, and 7. Number 3 is where my triple bond will be. So 1, 2, 3. Again, I'm just going to go left to right. So I'm going to put my triple bond there. That takes care of that. I got a dimethyl, which means 2 methyl groups, 1 at carbon number 2, which for me would be there. And 1 at carbon number 5. Again, 1, 2, 3, 4, and 5. And again, everything else here would be hydrogen. This guy doesn't need any. This one doesn't need any. This one needs 1, and this one needs 3. So it should look something like that. And again, you can put your methyl group up or down. It doesn't really matter. You know. Any question on any? Oh, you want to draw the line structure on that? Sure, we could do that. Let me just put it over here so I can look at it what I'm drawing. All right, so again here, if you did line structure, you could do the 7 to start with. So 1, 2, 3, 4, 5, 6, 7. If I got it, 1, 2, 3, 4, 5, 6, 7. We're gonna have our triple bond at number 3. I'm gonna go left to right again. 1, 2, 3, and that would be our triple bond there. Then we would have at number 2 a methyl group, and number 5, 3, 4, and 5. So it looks something like this. Yeah. You can. It technically is going to be linear at that part, but for us, it might just be easier to do the zigzag first and kind of add them in without putting in sort of the geometry part of it. It's fine. You can do it either way. But technically speaking, this part of it would flatten out, and geometry wise, it would be flat like a straight line at that point. The rest of it would be tetrahedral. So that's why it would be that zigzag shape with the flat. But for me, I'm okay if you kind of draw it like this, you know, like I just did, that's fine. But if you were thinking about the geometry, that little part of it would just flatten out basically at that point. Other questions? All right, questions on how to draw alkenes, alkynes.
When are you going to suggest or to write down the C's down or the months, or does it matter?
What are we talking in reference to, I guess? Yeah.
For that one, how she wrote the lines.
Yeah.
And I wrote the C's. Does it matter, say like an exam or?
It would. So these were a little bit more well, we're just naming and stuff, but it would ask you to either draw the condensed structural formula, the condensed formula, which would be this. It would ask you to draw the line structure, which would be that, or it would ask you to draw the structural formula, which you just draw out all the hydrogens. So within the question, it would probably specify which type to draw, and you should draw it that way. Technically speaking, if it doesn't sort of clarify, you could draw any structure you want. But on an exam and stuff like that, it will probably say something like draw the condensed structures for these or something like that. Yep. Other questions? Okay. So cycloalkenes, again, as I mentioned, are named with the ENE. When they do have, though, a group attached, you do need to give the location where that group is. Again, is in this case, because the double bond will take the priority. Now, when you have a ring that is shown there, this would be cyclopentane, but it has the double bond, so it would be, as you see there, cyclopentene. Now, we do need a number where this guy is located, because unlike in a cycloalkane, it has a double bond, which is the priority. So we could number it one of two ways. When you number a cycloalkene, you have to number and then go through the double bond. So what I mean by that is you have basically two options. You could start here and go clockwise, which would go through the double bond, and put that guy at carbon number 5. The other option is you could start here. I'll just go inside. As that number 1, go to the left and go counterclockwise. And we went through the double bond, and that would be carbon number 3. So clearly we still are looking for the lowest numbering. So in this case, we would want to go counterclockwise, with actually this being carbon number 1 and going counterclockwise to get us to 3. The one thing that you should not do is go away from the double bond when you are numbering. So if you started here, you should not go 1, 2, 3, and 4 because you did not go through the double bond. So if there is a double bond in a cycloalkene, you do have to number, you have two options, but you always got to number through the double bond. And then whichever way gives you the smallest number. Question on that. So obviously this would be 3-methyl cyclopentene, starting here, going through the double bond, gives us 3. Obviously going the other way, we ended up with 5, I think, as we went the other way. And that would be 3-methyl cyclopentene. You do not have to give the location of where the double bond is in the ring. It's always assumed to be carbon number 1, but you do use it to figure out what the number is of the other group that's attached, or other groups that are attached when you number it. Any questions on that there? So why don't you give this a go, see what you come up with. That's a 6-member ring and a ring type structure. It's a cyclohexane. We got our double bond, which will now turn it into cyclohexene. Yeah. And again, there's nothing else attached, so you don't have to obviously put anything else. And again, because it's a ring structure, you don't need to give the location of the double bond. It's assumed it's number 1, wherever side it's on. Any questions on that one there? Here, this would be our main part here, and that also is a ring structure. And that is based off of 5, so that's cyclopentane. Once again, we have a double bond, so that's going to be cyclopentene, ENE. We also have 2 groups attached to this particular one, and they are hanging off right there and there. And there are just lines, and again, lines in the line structure. So that is 2 methyl groups in the same compound. Dimethyl action. Need to give the location of it. So this would be carbon number 1. That would be carbon number 2. And that would be carbon number 3. Your other option would have been to start over here at carbon number 1, carbon number 2, carbon number 3, 4, and 5, which is obviously bigger numbers. Now, in this particular case, I did 1 and 2. Even though you could have got go through the double bond to do that, so we couldn't do that. So this technically should be 3, and we would need both numbers since they're both sitting there. So this would be a 3, 3 with the comma between the 2 numbers, dash dimethyl cyclopentene. Yeah. Question on that one? Yes, sir. Could you, so if your question is, could you start counting where the methyl group is? You would not do that in this case because it has a double bond. So it takes the priority. So you want to start the double bond in this case. Other questions? So again, double bond, triple bond priority, got to kind of definitely start there if it's in a ring structure, or give it the smaller number if it's a non-ring structure. Any question on those guys there? So some of the consequences of a double bond is that we create a certain type of isomers, which are known as cis and trans isomers. When you have a single bond, like you have in an alkane, you have what is known as free rotation around the single bond. I don't know if you built models in lab or not. If you did, you could take the single bond and just twirl it around. It'll just rotate all the way around if you do that. What happens when you make a double bond is you essentially will lock everybody into place. You lose the ability to rotate around that double bond. It pretty much just locks in. The result of that is we get certain groups that end up being on either the same side of the double bond or opposite sides of the double bond. And that's basically what cis and trans means. Cis means same side. And we're again talking about the same side of the double bond. Either they're both up above it or both below it. And trans means that they're on opposite sides of the double bond. And again, that means basically usually one up, one down, or opposite in terms of that. Or I guess if you do your thumbs and stuff like that. Now, there are a couple of things that you have to make sure of in order for a cis or trans isomer to be even possible. And that is pretty much, you should always look at the double bonded carbons. So you want to look at the double bonded carbons, and you need to have on the same carbon different groups. So you need different groups on the same carbon. And on the other carbon, you also need different groups. No, just in general, to have a cis or trans isomer, you need to have different groups on each of the carbons. But you also need, that's the same on opposite. So in my case here, A is the same. And actually B, same as B. And in this case, this would be cis or trans. This would be cis. The A's are on the same side, or you can even look at the B's. The B's are on the same side as well. But that's what you need to make sure. The double bonded carbons need to have two groups that are attached that are different to each other. And then when you compare between the two carbons, you need to have somebody that's the same. When we're doing cis or trans, even hydrogens can be considered like a group, even though we don't usually consider a group, but when you're kind of looking at it, you can consider it. So for example, here, if we look at the carbon-carbon double bond here, carbon on the left has a chlorine and a hydrogen. Those are two different groups, so that's good. Carbon on the right also has a chlorine and a hydrogen. Those are two different groups, so that's good. And they share the chlorine group. That is the same on opposite carbons, and they happen to be on the same side of the double bond. So this would be our cis isomer here. This guy here, same deal. The chlorines end up being on opposite sides, which means it is trans. So if you have the two of the same groups on the same carbon, you cannot have cis or trans isomers even possibility. It eliminates that possibility. So when we look at this, we'll look at this guy here. If we were going to name this, this has two carbons, which is based off of ethane. So it is ethene. It has at carbon number 1 a chlorine, and carbon number 2 a chlorine. So this is 1,2-dichloral ethene. And because this is cis, they typically will just put cis in front of it. So cis 1,2-dichloral ethene. This would be the exact same name, except that it is trans 1,2-dichloral ethene in this particular case. All right. Let me see here. All right. So let's take a look at these guys here and see if we can identify them as cis or trans. So first off, A, is it cis? So again, we would want to focus on the carbons. This group and this group are different. This group and this group are different. The chlorine on each of them are the same, and so is the CH3 on each of them are the same, and they are on the same side of the double bond. So this would be cis. Yeah. Guy here would be in the middle. Would be trans. Again, looking at this guy, different groups. different group, same group, which is bromine or the methyl group, and that would be trans. And this last guy here would be, this would be trans as well, these guys being opposite of each other. What would this one be? Is that a question? I say none, neither. Because when we look at this carbon, this group and this group are different. This group and this group on this carbon are the same. So that eliminates the possibility of cis or trans. So you can't have it in that case because you have two groups that are the same. So you got to make sure you do have those different groups. And lastly, by the way, what would the name of this guy be? Longest carbon chain is how many? I heard 2 and I heard 4. So it actually is 1, 2, 3, and 4. So sometimes when they're drawn like this, people just look at the double bond and go 2. But the longest carbon chain here is actually 4, which would be based off of butane. But because of the double bond, that would be butene. And in this case, the double bond is located at carbon number 2. Yes. So that would be 2-butane. And it don't matter which way you go on that, you can get 2 either way. And that would also mean that we have a chlorine on carbon 2 and a chlorine at carbon number 3. So this would actually be 2,3-dichloryl 2-butene. And to make it all nice, we would put cis in front of it. And this would be cis 2,3-dichloryl 2-butene. So it's really important when you look at something that's drawn as cis or trans and you're asked to name it, that you just don't look at the 2 carbons and go ethene every time. You still want to make sure you look for the longest continuous carbon chain. And again, it will probably go up or down and up because it is drawn cis and trans. So it's a very common mistake people make by not finding that longest carbon chain. And again, in this one, if you looked at just this one right here, same thing, 1, 2, 3, and 4 would be the longest carbon chain, and 1, 2, 3, and 4 for that one as well. Any questions on that there?